Welcome to Made in Science, the official podcast of the University of Stuttgart. My name is Wolfgang Holtkamp. I am Senior Advisor on International Affairs at the university and your host. Today, we welcome Professor Markus Bühler. He is McAfee Professor of Engineering at MIT and, of course, a former student from the University of Stuttgart. His work ranges from computational mechanics to bio-inspired design, manufacturing, and experimental analysis. Plus, he has also become an artist, but more about that later in our conversation. First of all, we are really so glad to have you with us today.
Well, thank you, Wolfgang, for having me.
For a start, let's talk about your work that you are doing right now. Your particular research interest lies in the mechanics of complex hierarchical materials. Please, could you tell us what that term really implies?
Yeah, sure. And actually, it's something that I started to become interested in when I was a student here in Stuttgart, and maybe we'll talk about that later. So what I'm interested in is to understand how materials work at the macro scales. What are the things you can see with your eyes, things we can touch and see with our hands and as humans, what these properties are based on the chemical structure. So I'm asking the question, if you think about a material and it's very deformable or very strong or very weak, where does it come from? If you look at the chemical interactions between the atoms, you can actually build models to predict ultimately how the macroscopic features of the material derive from the quantum mechanical chemical bonding and interactions. And there's lots of different scales, we call them, in between, right? There's the molecules, there's groups of molecules, there's fibers, and so on. My research tries to predict how these different scales are relevant for the macroscopic properties. And that obviously has really strong implications for engineering, right? Because most engineering applications, even though we build things at the nanoscale, but most of the things we build are at the macro scale, so we can use them as humans. Our scale is not the scale of individual molecules. We usually deal with vehicles, batteries, buildings, paint, coatings, implants, biomedical applications, and so on. They're usually at the macro scale. And so my research tries to connect how we can make better products by engineering individual molecules and atoms.
What particular methods do you use in your research to really find out about these molecules that form our world? Is there any particular method that you perhaps also rely on especially, or is there a whole bunch of methods that comes up with every new idea that you have?
Well, good question. So the main method we've been using for the last, I would say, decades now, it's pretty shocking, but I've been doing this for a couple of decades now, is what's called molecular simulations. And that actually is a tool, as I alluded to earlier, that actually started being exposed to when I was a student here at the University of Stuttgart in Professor Haas's lab, institute at the time. We can talk more about that later, but that is the tools. And what molecular modeling, molecular simulations, molecular dynamics, there's different terms for basically the same thing. What that does essentially is to predict how individual atoms move in a material using computational simulations. I use lots of computers. Usually we use big computers, because we have, if you think about materials, they have billions and billions, trillions of atoms. So to solve these equations requires significant computational power. But that's the main workhorse of simulation we use. So we're trying to watch the individual atoms do what they're doing according to the physical laws or quantum chemical laws, if we're going all the way to the nano and quantum scale. And then we observe them. We use a lot of statistical methods to analyze what these behaviors actually mean, because if you follow just the motion of atoms, you can't directly say what color a material has necessarily or how strong it is. You need to do something else. And we do a lot of technology or technique development in making these connections to actually predict from the motion of atoms what kind of properties materials actually have. That's the main method. Now, this was something we've used for a couple of decades, but now in the last several years, we've also gotten very heavily into machine learning, or I think in Germany it's called KI, Künstliche Intelligenz, AI, which has changed the way we model things. So instead of following necessarily physical laws, we simply observe the behavior of systems, and AI methods can then derive engineering laws or solutions or predictions directly from observing data. And that's been a big transformation that I've been involved in since the last 5 years or so. So there's always something new happening. It's not happening for every problem, but there are definitely innovations happening. And the last biggest one in the computational material science world has been the AI revolution, and that brings sort of a new set of tools to the table. One thing I want to also mention, if you're looking at material behavior, engineering behavior from the atomistic scale, you can use the same method for pretty much any property you can imagine, because any material, whether you use it again in automotive industry as a battery or as an implant, everything consists of atoms and molecules. And so if you're beginning to describe your material at that scale, you're very flexible. And that also explains, if you look at my publications and my collaborations and my funding and my application areas in general, you're going to see that I work in lots of different industries, lots of different application areas, because the method is very flexible. The other thing that makes it pretty wide-ranging in the application space is the fact we look at mechanical properties, especially failure. So we're interested in seeing how materials perform under extreme mechanical deformations. And pretty much anything we have in this room, even from the cell phone screen to my sunglasses, it's going to have some mechanical integrity. Otherwise, the material will just simply fall apart. Our computer chips is the same thing. They're amazing devices, amazing small nanotechnologies, but they have to be mechanically stable. So if your computer heats up, there's stresses that develop. So you want to make sure that your integrated circuits, your microphones have mechanical stability. So mechanics and failure is something that's really very widely seen. And I have lots of collaborations in academia and with industry where we study precisely these aspects. And so sort of combining atomistic simulation, very foundational, with an area that's very important for lots of different application areas, mechanical properties. I found a really exciting area that has lots of touch points. And I like to work on different areas because I'm interested in seeing the analogies and synergies between different areas of application.
The different areas remind me of an interdisciplinary approach that your research is very, very much influenced by. How did that evolve? Did you see that coming early enough, or really early in your research work, or in your career for that matter? Or is this something that has taken momentum over the last, years only?
Yeah, so I've always been interested in lots of different, I would say, areas. And I remember actually when I came as a student here to Stuttgart, I studied Verfahrenstechnik, chemical engineering, and I loved math, I loved chemistry, and that was sort of the combination for me. And of course, over time it evolved, but I've always had an interest in sort of basic science, mathematics, foundational principles, but also in application areas. And if you work in this space, engineering is sort of a perfect arena kind of for you to work in. And I think the fact that we have the challenges we have today in addressing technological innovation, you need to work in multiple disciplines, because if you want to build a better battery, you're going to have to know about chemistry. You also have to know about the vehicle you're going to put it in, and you have to know a lot of times as engineers today about social implications and ethical implications. Right? Do you want to build that device? Is it ethical? What are the implications for policy, or do you need new policies? And so I think for engineers, we have all become much more interdisciplinary, I would say, but I've always had this great interest. And in fact, that's one of the things that drew me to chemical engineering in the first place, but also drew me ultimately to MIT, because at MIT we have this philosophy where we like to have no or few boundaries between disciplines. Right? So I have appointments in mechanical engineering and civil environmental engineering, and I have students actually from many different departments and programs. Chemistry, I've had students from biology, biological engineering, material science. I've had students from many different disciplines, and including, as you mentioned earlier, in the arts. I work with people from the humanities as well, scholars in that field. So MIT has been an amazing place sort of to foster this interest, and I think, as you alluded to, I think in the last couple of years we've seen a real need actually for engineers to be educated across not just in our own technical disciplines very deep, we need that of course, but to also learn a much broader perspective. Right? If an engineer goes out today in industry or in policy or in universities, they're going to have a much broader perspective as, say, 20, 30 years ago, where they were basically just doing technical work. Now it's not enough, right? Communication is another topic that I also, especially in my administrative work at MIT, I've worked with communications teams, and it's important to you, how do you communicate technological innovation to donors, sponsors, investors, but also to the public? If you want to create a new technology where if the population is afraid of that new technology, you're going to have a problem creating this product or marketing the product. So I think we all have become much more aware of these multiple disciplines, and I think scientists, just have to work together with other scientists and engineers to solve problems. It's no longer enough to be an individual scientist sitting at a desk for years and solving a problem. You need to work and have insights from lots of different areas.
I would like to elaborate on that a little more. I wonder if students who come to MIT actually come to this university because they know there is this broad approach in particular favored. So the question would rather be, what do new materials and mathematics and structures of music and language really have in common? And how do you employ the insights from these very diverse areas into your research? Can you give us an example on that?
Yeah, sure. I'd be happy to give examples. So in terms of students coming to MIT, I think they clearly value the multidisciplinary environment, and we have just an illustration or an example that gives sort of a good idea. All the students at MIT, and I think also in Stuttgart, even when I was here, I had to take humanities classes, but we at MIT have a very strict requirement. You have to take all the engineering and science requirements, but you also have to take humanities classes, language or culture or music or things like this. And the students that we get at MIT are usually interested in multiple dimensions, and they know that we value this because we have requirements for them, but they also live that in all the things they do. I think we have that culture at MIT, and it's something that when you walk in and you meet the students, you can tell they're not only interested in in an island of knowledge, but they usually are interested much broader. And when we work with undergrad students in particular, or grad students or postdocs or faculty, you're going to see that all across the board. And that's really fun, right? Because you have lots of people that have intersections in areas you might not expect. So in my own work, we came to this. So I'm basically, I call myself a material scientist. That's what I became ultimately at Max Planck when I did my PhD here in Stuttgart. And so in material science, you have the central dogma, if you wish, is basically you have a connection between structure, and you want to think maybe about a process to make that structure in an experiment or in a factory, and a property that arises from that. And so that is something that we typically write it out as maybe what you call a recipe. How do you make steel A or B or C? How do you make that polymer? You kind of have different chemical processes and conditions, and then you get a structure. And that is kind of similar. It's a process where you can imagine it's like a little booklet that you write to describe how to make that material, and then you can, if you're a material scientist in theory, you study how that property that you might create actually where it comes from. So you might learn from that it comes from particular grain sizes or a particular type of polymer chains or crosslinks. And those of you in the technical areas, you'll be familiar with those terms. So it's examples for what the design at the nanoscale, the mesoscale looks like. And then you understand perhaps that certain relationships are because of physical laws, like scaling laws, fundamental laws that give rise to certain properties, and that's what engineers then use to optimize materials. So that's sort of it's like a story you tell. And that's something that we actually started capturing these stories in quotation marks using mathematical concepts called category theory. So it's a categorization where you basically begin to say, you systematically write down these recipes of how structure, function, and processes relate to one another. And we then also had a longstanding interest in my own work in my lab at MIT in other areas. And so you begin to see that, of course, if you think about, for example, music is an area I worked on a lot, or the language of music, you have similar types of laws and rules that create certain types of functions. And in music theory, that's an area where that is studied, actually, how certain types of sounds and instruments and scalings and rules to form certain types of melodies and chord progressions come about. So you can begin to see the analogies. And music is a very mathematical concept as well, if you wish. Of course, there's an input there in human creativity, But ultimately, you can also apply a theoretical framework, and you can begin to see in all of these, you have building blocks, we call them ultimately. So in materials, it might be an atom or a molecule or a protein or an amino acid, which makes up proteins, depending on what perspective you take. Right? So you can look at this from different perspectives. But let's say you take a look at atoms and molecules. Those are your building blocks, like Legos, and you can build really interesting things from that with very interesting properties. And in music, you can see the analogy would be where you have a note, for example, 1 instrument, 2, 3, and as we look at a musical score, you can understand how function in this case is an audible experience for a listener emerges by using these building blocks. The Legos, in this case, are notes and instruments, and you can put them together and forming lots of different expressions. And if you use mathematics of category theory, you can begin to analyze them systematically, and you can begin to say, okay, here I have a category of a material A, and here I have a category of a musical piece, and you can begin to see what are the similarities and differences between them. And we have sort of done this for many years. In fact, I think we started doing this more than 10, 15 years ago or so. And in the last several years, we've made lots of advances using machine learning, because one of the things you see in this area is that it's a very high level of complexity. Many problems, however, are much more complex than problems we can treat analytically. And so that's where computational methods become very, very powerful. And so what we've done in a nutshell, essentially, is to analyze how we can translate materials into, for example, music or audible form, and also how we can use existing music and translate them back into materials. Right? And so that sort of two-way translation has been quite interesting, and again, enabled by advanced computational methods in machine learning, especially techniques called language models. So these are models that basically deal with language. And so descriptions of how things work, and mostly language models are applied maybe in your iPhone or in your cell phone, because you can communicate with your cell phone, it will answer you, or maybe computers can write stories for you, or they can draw pictures for you, but we have translated or applied developed methods within the same scope of course, sort of technological level, but now applied for materials, and especially at the interface between materials and languages that describe materials on the one hand and also music on the other side.
Those of us who want to meet the scientist, Markus, will find that you have a very, very high citation rate already. Those of us who want to find the artist, Markus, will have to go, for instance, to the Guggenheim Museum or to the Palais de Tokyo in Paris. You talked a little bit about the connection between science and the arts, and how those areas actually are not strangers to each other, but that perhaps it is often up to us to understand the links between these. What is it that was exhibited or is still being exhibited at the institutions I mentioned, or perhaps somewhere else that I don't know?
Yeah, sure. Well, so I've had these collaborations have really been created at MIT in a group called CAST, which stands for Center for Art, Science, and Technologies. MIT has a center, or an institute, if you wish, that fosters exactly what you describe, relationships between art and science. And it's a very flexible setup. We have artists coming to MIT. We have MIT faculty working with artists. We have MIT faculty creating art together with visiting artists. And so a lot of the things you've talked about, some of the things were created in that setting. So all of these things have been created through CAST, essentially, and catalyzed through that. So at a Guggenheim, that was during the pandemic, so it was a virtual, it ended up being a virtual exhibition. So I don't know, I think it's probably still on the website, because it was a virtual creation, because at the time everything was shut down. And so I worked with the visiting artist. We created, so I talked earlier about analogy between sound and material. One of the ways by which we can create this analogy mathematically and physically rigorous actually is by looking at the vibrations of molecules. And so that's sort of I didn't get into that detail earlier, but it's not just a description. It actually has a physical basis in that every molecule, if you look at it, even if you were to look at it using a very powerful microscope at very high time resolution, you would see it actually isn't just a static picture. If you imagine your chemistry textbook, right, you open it and there's a picture of a molecule in there. And I always say that's a wrong picture, because molecules aren't actually static. Like this chair is the same chair now, and in 5 minutes probably it's going to have the same shape, unless the sun melts it because it's so hot. But usually in a room temperature, the shape of things won't change. But molecules are very different. They actually are continuously vibrating and changing. So it's like a guitar string, except nobody's actually plucking the string. It's just by the kinetic energy of what we call temperature, it's enough to deform the molecular bonding structure significantly. And so those are features that are well understood at the quantum level, molecular level. And so that is a feature that we can actually study and ultimately make audible to the human ear. And so what we've done in that particular work, we created these models of how molecules sound like. And then we wanted to make it visible again. So in other words, you can listen to it. But sound waves, of course, also have a physical quality to them that they can actually deform, air, of course, but if you play sound waves loud enough, if you wish, you can also deform other surfaces like water, for example. And so in this more artistic work, we sort of tried this experiment. So it's a science art experiment, so it doesn't really follow the scientific method fully, but it also is also, of course, art that is not just creative, it's also art that's informed by science. We created these vibrational patterns of molecules using scientific methods. And then we play them on a water surface, and we create water waves, essentially. So the water waves are usually created by wind or earthquakes, maybe. But in this case, we created them using sound waves. And so depending on what kind of molecule makes the sound originally that we then play to the water waves, we're going to create different wave patterns. And the question we explored is, can an AI algorithm determine what molecule caused these wave patterns? Because, of course, for the human eye, it's too complicated. We can't really distinguish these fine details, but an AI algorithm can actually pick that up. And so then we created these wave patterns. So we basically had, so again, the connection is the nanoscale vibrations, make them audible, play the sound vibrations to waves, as waves to a water surface, which then again creates water waves. So we could see how these different molecules create different water waves. The algorithm then has learned to distinguish them. Now, that is sort of a skill, again, that's hard for humans to do, but an AI algorithm can do that quite well, actually. So then we did this trick where we said, what can the AI algorithm teach us? And so we basically gave the AI algorithm other types of wave structures, maybe waves at the ocean, and my collaborator actually took a video of waves at a beach in Norway, and then we asked the algorithm, what kind of molecular vibration equivalents do you see in these other water waves, which are not created by molecules, obviously. They're created by wind and, I guess, other forces in nature. And then we can draw these patterns on top of these other objects. We also gave it pictures of rocks or trees and things like this, and basically asked the algorithm, what kind of molecular features do you see in these other things, and are there analogies and similarities? Now, this is sort of the scope, and to show the connectedness really across different manifestations. Again, you have invisible things at the quantum level you can't see, we can make them audible, but then you can ask, where else are they found? And this question that I'm exploring a lot of times in the research is the universality of relationships, and that's very powerful for engineering, actually. So you ask the question, it starts out, but this perspective actually is very important. If you are an engineer and you want to solve problems, if you look for the solutions always in the same space, you're going to run out of ideas at some point. And so this allows you to say, well, if I have a solution to a problem maybe in a discipline A or B, I can maybe apply this knowledge in another discipline. And that's what interdisciplinary research allows us to do, and the art-science collaboration in this space formalizes that. And in one way, of course, it creates scholarship in the arts, and it creates things we can exhibit, we can tell stories around it. I mean, in the piece we ultimately created, we had a whole story around this theme, explained to a general audience the connectedness of waves and wave patterns from the nano exactly to the macro level. And we can also use this knowledge to train students.
Markus, from what we have heard from you already, and certainly from what I have seen at MIT and beyond, you are somebody who inspires people. Not in the old-fashioned top-down way, but in the motivating way of somebody who believes in the potential of everyone. The example that I have in mind is certainly a hackathon at MIT some years ago that I remember on the morning of the day, very early, you sent me an email saying, Wolfgang, you have to come. And that was my first hackathon ever, really, to attend. And it was, for me, very fascinating to see that everybody speaking, professor or postdoc or doctoral student or master student, would have 5 minutes for the presentation, period. And they all, including yourself, found that what they wanted to say, they could do it in 5 minutes. And it was all good. So you managed on that day to inspire people to get connected, to find out who else at MIT is working along these lines or would see connections that you have just talked about. So you got people started. And I wonder, what did it take to get Markus Bühler started? When was the click moment, or perhaps a series of moments that you recall in hindsight, saying, yeah, without those turns, I wouldn't be sitting here in this podcast today?
Well, I think it all started when I started taking classes here, Vorlesungen here in Stuttgart, and I remember especially mathematics lectures, and of course all the engineering disciplines too, but particularly mathematics, which was, for me really a moment where for the first time felt, and also meeting my peers, my kommilitonen, I think, call them, where I felt like I found a place where a lot of people that think like me and have interests like me. So one of the special things that I saw, in addition to meeting like-minded people here and being able to participate in classes and lectures here, Vorlesungen that were really interesting and really drew me in. I could dive really deep into the topic, which I'd never had a chance to do in gymnasium. I never really had the opportunity to go that deep. And so that was sort of a moment that also was complemented by things I could do as a Hiwi at the time, research assistants. I was a Hiwi and at Fraunhofer, I think in the beginning, and then I did some Hiwi work also for the Mechanics Institute with Lothar Gaul at the time. And then later on, I became a teaching assistant for Wolfgang Wendler in mathematics, which was really exciting for me, as I was one of the very few engineering students, actually, who were TAing in the higher mathematics lectures with him. And I learned a lot, of course, being exposed to really high-level research and being exposed to teaching students and as a TA, as a teaching assistant. And that was sort of the moment then where things really started to open up for me. And I then became interested in going abroad to Michigan, spent some time at Michigan Tech. And right before I went to Michigan Tech, which I mentioned earlier, was a course I took by Rajan Rapic, who is now, I think he's in Kaiserslautern, maybe he has moved, but he was I think a senior doctoral student or a Wissenschaftler in Professor Hasse's Thermodynamics Institute here in Vaihingen, and he offered a special lecture called Atomistic Simulation or something to that effect, or Statistical Mechanics of Chemistry or Chemical Engineering. So this was in chemical engineering for Fans techniques. It had to do with phase diagrams and things like this. And so anyway, so Rajan Rapic taught this course, and he taught in that course about atomistic simulation. So how do you predict phase diagrams not by making a measurement, but actually using a computer simulation? And I loved that, and that sort of opened up. That really was the trigger for me, and I still do the same thing today. As you asked earlier, what's your main method? Atomistic simulation, that's sort of what I've been exposed to for the first time here, and that's something that I took as an elective class. Was not required. It was something that I took right before I went to Michigan, and I absolutely loved it. I actually didn't use this in Michigan at all. I did research in Michigan on what's called smart materials. It was very amazing, and I did actually go to conferences, wrote papers for the first time and all these things. But when I came back to Stuttgart for my PhD at Max Planck, I began to use this atomistic simulation again. And I was lucky, actually. And this is sometimes the heavens aligned in some ways that I came back here and I had this offer to go to Max Planck because a new professor had joined from Stanford, Hua Zhenggao, who was my advisor, who became my advisor. And he just moved from Stanford, was building his lab here, his group at Max Planck. And he started doing atomistic simulation of fracture, material mechanical behavior. He was a mechanical engineer, material scientist, mechanical engineer, which I am now too. And so he was interested in having students working on this. I met him. I met some folks at his lab, and I told them about the course I took, and sort of one thing happened after another, and I started doing my PhD then there, and it was extremely exciting because I could actually combine the mechanical engineering things I had learned, especially in Michigan. I worked on solid mechanics. That's a Festkörpermechanik, I think in German. I combined that with the atomistic simulation materials I had learned in Jadran's course, and also in, of course, Professor Hasse's lectures in thermodynamics and chemistry. So things sort of came together in this journey, and then on, I went on to other places and things. But that was the moment, and it was sort of the intellectual community here at Stuttgart, which was something I had just never experienced in my life. It was eye-opening and mind-opening, you can say. And then having opportunities to be exposed to high-level research and teaching, which I was very thankful for. I'd never been given opportunities like this before.
After Stuttgart, you went back to the United States, and you have taught at various universities, both West Coast and also East Coast. From that experience, how did that reflect on you? I would expect there could have been very different research cultures, perhaps, at the various institutions. And I might conclude that you draw, your lessons and came to your own convictions how to proceed. Sum up everything that you kind of experienced at the various learning spaces in higher education that you had a chance to be in. What did you take from that, and how, and what is still in that, I guess, at MIT as you live it and love it and present it?
Yeah, so great. Yeah, no, I've had the chance to move around a lot of different places, and I always would encourage all of the younger aspiring people, whether they go to academia or industry or anywhere, it's good to move around and see different cultures of how things are done. And in fact, that's one of the things we do also at MIT. One of my roles is as faculty director for MIT Germany, MISTI, and we have a program with Stuttgart as well. And that's one of the convictions that I have, actually, is to give young people the opportunity to go abroad from MIT, to come to Stuttgart and experience what things are like here. But so what have I taken away from different places? So I'd say, after my PhD, I went to Caltech, and I actually went there with a very strategic kind of mindset. I had, the experience in chemical engineering, I had the experience in mechanical engineering, I had my PhD in material science, which was actually formerly in chemistry. All the PhDs at Max Planck with my professor was given in chemistry. And I wanted to know more about the quantum level. So we talked earlier about the quantum vibrations of molecules, and I wanted to work with a professor that had a lot of very deep experience in that field, and so I ended up working with Bill Goddard, who's still actually active at Caltech. And his lab, he's a famous person in quantum molecular simulation, and what I talked about earlier, the scale bridging in the very beginning, you asked what I do. He's been doing this and pioneering this since the 1970s and 80s, so he has a long history there. So I wanted to work, basically I thought, why don't I try to work with somebody who's the best in the world in this particular field? And so I ended up being very lucky, actually, having a chance to have a position in his lab. So work with Bill, and then, of course, because I had published some really, in hindsight, looking back, I had published some important papers. I didn't know at the time. At the time I thought, of course, when you're applying for jobs and you're looking around as a postdoc, you're struggling. But I had published some papers that had quite a bit of an influence, and so there was a lot of people paying attention to me. And one of the places that actually looked at me as a potentially hire was MIT. And so very quickly after I moved back to the U.S., worked at Caltech, I had lots of universities contacting me, why don't you come give a talk, we have a position. And MIT was quite persistent, actually. They invited me and they said, hey, you should apply for this job. And they were really interested in recruiting me, so they ended up recruiting me. And so moved from the West Coast to the East Coast. And then started working at MIT. Now, Caltech is a very small university, a couple hundred faculty, thousands of students. MIT has 10,000 students. That's sort of almost a magnitude smaller than MIT. And Caltech had a very collaborative culture. We had at Caltech, there are divisions and departments, faculties, but there really are only names because people work across disciplines very strongly. They have to. If you imagine being university like Caltech, and you want to be in the world's best ranking and problem solving, you're going to have to take all the faculty you can and make them, like you said earlier, make them effective, make them work together, solve problems, seeing the potential in how you can put different people together in a team to solve problems. I was lucky to be part of a larger team, actually. It was called DARPA Prom, which dealt with predicting material properties, in fact. And so there was a team that had mathematicians on there, chemists, material scientists, mechanical engineers, and so on. And it showed me that. Now, when I moved to MIT, MIT is a much bigger university. We have lots of people in the same field in multiple copies, if you wish. Not exact copies, but we have similar faculty, and maybe unlike the German systems or the US systems, very much based on individual faculty. So there's no institutes. There's departments, which are like faculty, so they have like 30 or 40 faculty in them. But each faculty is their own little enterprise. We all have to raise our own funds. We all decide what to do, pretty much. In research and teaching, there's some top-down kind of telling you what to do, but in research. But yeah, so at MIT, we had lots of faculty doing similar things. There was a little bit more division, but a lot more opportunities, of course, than at Caltech. So I like that. And then we had lots more students. I remember when I went to MIT and I had the chance to work with undergraduate students there that are extremely bright, extremely interested, diversely interested, like you were asking earlier too. And then I built my lab there essentially. And starting from just myself, I was the only one in the lab. I had 1 or 2 PhD students, and then I had a couple undergrads, and then now I have about 15 total. I had a bit more, close to 20 at some point, but usually there's a limit on how much time you can spend. So in the US, the individual labs are there's a very close collaboration, interaction between the faculty, myself in this case, and students. So there's not a desire to have kind of hierarchy of different people that basically the students never meet the PI. The expectation is at MIT that you as a PI will have the time to work and meet with everyone and actually interact with the students. And so there's a time limit, of course, if you want to do that well. So about 15 students or so is something I found to be optimal for me.
And for those whom you cannot meet or who cannot meet you, they can find you because you also offer TED Talks. What are some of the topics of these talks that you offer, and which ones did you like best?
So I've given a couple of these TED Talks and also other general audience talks, and one of them was actually during the pandemic, we talked earlier about the art-science connection I worked on. We've translated lots of different materials into music, but during the pandemic, we created a translation of the COVID pathogen into music, and that created lots of interest, of course, in the public domain. So one of the talks was titled "If a Virus Could Sing," and basically we talked about how you can listen to this COVID pathogen, and that was actually had a big impact around the world. So I've given lots of interviews, and one of the things I love to do is outreach, and so it was a great opportunity for me to talk to a general audience, let's say in a TV station or audio. I've given interviews around the world, and tell them, about music, which is accessible to everyone. It's a universal language, but also tell them a little bit about what we talked about earlier about vibrations and mechanics and how proteins look like and how they work. And so that's something that I like to do. Some other talks I've given the general audience is something about career advice sometimes, and just like you said earlier too, and thank you for picking that up. I'm very interested in inspiring young people, or not just young people, anyone, but especially young people, that are questioning what they're going to do with their lives, and showing them pathways. And I give lots of talks also in high schools, and I have a high school program, actually, a middle and high school program in my lab at MIT, where I invite, this year we had 40 or 50 students from local middle school, which is, I think, 7th to high school 12th grade. They spend time in my lab at MIT with teachers. And they try to do research, it's the first time they do that kind of thing, open-ended questions, but some of them are doing really well. So I do that a lot, and of course we have programs at MIT for very talented high school students internationally. We recruit. One of them is called the Research Scholars Institute, and they basically have an international recruiting process where they select the best of the best from around the world, not just from the Boston area like we do in my own lab, but And so I've had students from that program, and some of them have written papers with me. Like last year I had a student, and he wrote a scientific paper on machine learning and proteins, actually, which was just published and is having a big impact. And so I like to do things like that, and it goes from TED Talks to hosting high school students and middle school students in the lab and working with teachers. And I think there's and one of the reasons why I do that is because I feel like when I was a student here, and we talked earlier about when did it click for you, it was the moment when I was given the opportunity to do things like that. And for me, it happened only after I got to Stuttgart, basically. But I would love to have had the chance to do that earlier, but I didn't. But regardless, when it happens, but it's always great to have you need someone who's your champion, and somebody who believes in you, and somebody who gives you the opportunity. Like I had the chance to work with Huijian Gao as a PhD advisor at Max Planck, and later on with Bill Goddard and so on. And those are, special moments where they somewhat gave you the chance, right? And I want to give back to other people in that sense.
The particular MIT Germany program, the MISTI that we talked about earlier, works along the same line in a way, right? It is for one column is for the researchers, of course, but there is also the column where university students, MIT students, come to Stuttgart and actually teach in English language in the hard sciences subjects here in our gymnasium, and vice versa. We also bring students from the University of Stuttgart to MIT so they get to know the university there, but also they will have a chance to teach in Boston. And so that will be a new experience for them as well. These are teacher training students already, but to open up the mind and to see the other is, of course, the essential aspect. And we are glad that companies and foundations actually support this particular effort that you just expressed so well. Do you think, Markus, that not only for young people, science is at a particular crucial moment in time now, with challenges like climate change, with digitalization and consequences that we see the changes in our lives, in our daily lives so much, with the addressing questions of energy and how to proceed in that area in the future. Do you think there are, or these are, particular days for science?
Yes, I think science has become, obviously, it's always important for the advancement of society, but there's a critical moment, of course, right now to solve really pressing problems, as you outlined. One area I think we as scientists have to be better is explaining to the public better what we do and how we do things, and also make sure that the public understands. I'm a big believer in outreach and STEM, and give tech talks, and as you asked earlier, and that is really because I feel we have a responsibility as scientists. We're mostly funded, at least in my work at MIT, we're funded by public funding, foundations to some extent, also industry, but a lot of the funding comes from the government agencies like National Science Foundation, Department of Defense, and National Institutes of Health, and so on. And I feel we have a responsibility for the public to understand what we do and how we do it, and also something I'm very passionate about, not to talk down to the public and basically tell the public, okay, here's the result, you've got to believe it. We have to explain the process, and we also have to explain where the uncertainties are. And that's something that I feel we can do better, to be honest, because as scientists, all of us, because the general population is very smart. We sometimes think as experts, in quotation marks, that we just have to tell the public the answer and say that's how we're going to do it. But we have to do better than that. I think we have to explain the models and the predictions and the measurements in a lot more detail. And I think the debate that's going on right now around lots of different topics, climate and COVID and public health and so on, require, I think, a high degree of honesty, because there's a danger that the public will not believe scientists anymore if they don't believe that we're telling the whole story, meaning that if we're cherry-picking the results we want the public to hear, but not telling the other ones, then I think there's a danger there. So that's an area that I feel quite strongly about, and I think that scientists should be doing lots of outreach and public talks, because that's a way for the public to create trust in the scientists and vice versa. I think that's an important area. But yeah, science is clearly at a point where this is important. But I can also see that there's a lot of doubt in the population about science. I mean, I do not know exactly the discussions in Europe and Germany, but in the United States, of course, around COVID, there's been a lot of debate. Starting from COVID itself to vaccinations and everything, and I do believe we have to be prepared as scientists to engage much more with the public than we have in the past.
And how's the cooperation with companies going? You talked about manufacturing earlier,
yes.
And how important it is. You also have a number of patents out, and so how has that changed at all? Or again, in these times and days, is this a new moment as well that you see that the relations are need to be more fostered or need to be strengthened, or are they stronger than ever? I'm curious to hear about that.
Yeah, so it's another great question. I think for my own work, I try to pick problems that require a really, really exciting scientific foundation, right? And that's what I'm passionate about, doing science and advancing knowledge. But I also am very passionate about applying it to real problems. And for me, industry collaborations are exactly the space to do that. And I do this in a lot of different ways. I do this as a consultant on my own with industry. I do it at MIT, of course, with funded projects. And those have, I think, my own lab have grown a lot in the last several years, because I think industry is becoming kind of like the public. They want to know, and they want to squeeze out more performance at lower cost or at lower environmental footprint. And they realize that if they just continue tweaking existing technologies, it's not enough. And so they really need to think a little bit deeper. And a lot of industries have, even big ones have, of course, they have lots of expertise in-house, but when you want to go across different disciplines, it's hard to build an entirely new group in a new area that you don't fully understand or appreciate or have a lot of background in. So they come to universities a lot of times to create this multidisciplinary perspective, because we have very easily can collaborate across engineering disciplines, science disciplines, even humanities and social impacts. And they come to us for that, and we've seen an increase actually in that. And so in my own lab, or at MIT broadly, we have seen a significant increase in industry funding, foundation funding, less government funding. And generally we're very lucky at a place like MIT. We were attracting lots of interest, of course. And as I know Stuttgart does as well, you have amazing industry close by. By the way, one of the reasons why we were so keen on having Stuttgart as a partner for MISTI, because the kinds of industry connections you have, and I also benefited from that as a student, especially at Fraunhofer Institute, were absolutely phenomenal. But yeah, so we've seen this increase generally in creating and having industry becoming interested in finding knowledge and expertise in areas they don't have. And also, they want to know what is going on in the cutting edge. So if you're, I mentioned earlier AI, machine learning, KI, that's an area we've gotten into about 5-6 years ago. And for us, it was a slow transition into that. In the meantime, there's been a revolution. Everyone's talking about it right now. A lot of industries are being reformed based on this. And again, that's an area where we have acute interest a lot of times, because a lot of legacy, big industrial, small and big companies, big brands, small brands, niche brands, they want to know, what is this all about? What are the risks? And here's another example of hype. You have the news. If you open the newspaper every day, you have an article about how amazing AI is and how it's going to revolutionize everything, from providing solutions to climate, to batteries, to driving cars. That's a much more subtle discussion that we need to have around it. So the press, of course, wants headlines and clicks, I guess, on our phones. But yeah, so for industry, this is a big issue, that they want to know really what are the positives, the negatives, the concerns, what are the implications beyond the hype. And a place like MIT, we go very deep in the topic, and so we've seen a great interest in industry collaborations, I think because of that.
Markus, Coming to the final part of our conversation here today, which I've enjoyed so much already. Now we have moment 7, which basically means we will ask 7 questions and we would like you to answer as shortly as possible. Moment 1. Spätzle or Maultaschen?
Both.
Moment 2. One thing you could change about the world?
Better communication.
Moment 3. Markus, do you have a book recommendation for us?
Well, not a book recommendation, perhaps, but maybe a music recommendation. You could all listen to some of the virus music we've created with the Lindenbaum Orchestra in Korea that actually has created an audible representation of the interaction between the spike protein in the COVID pathogen and the antibodies in the human body. And this music was created earlier this year to express the hope that maybe now we'll be finally moving on from the pandemic into a more normal environment.
Moment 4. The best advice that you have ever received was?
To ask questions.
Moment 5. Your favorite place on campus at the University of Stuttgart?
It was the cafeteria in Vaihingen. I don't know exactly the name. Maybe it doesn't have a name, but it was the place where we would go between lectures and sometimes do assignments and prepare for the next course. And I remember drinking coffee and eating the baguettes they had. I don't know if they still have them, but that was a favorite time actually, because we would sit there with a group of students and discuss, and that's one of my favorite memories. And in the summer, we'd sit outside, of course, but in the winter, we'd be inside.
Moment 6. If I could start all over again, I would do the following differently.
Well, I would probably ask more questions. That's what I said earlier. That's something I would start earlier. And I believe that the journey is the journey, and you can't really recreate the journey because then it would be a different journey. But I think I would probably tell myself to have more courage in trying things I wouldn't try. So for me, when I came to Stuttgart, I was for the first time trying lots of different things and exploring the university and knowledge in different fields. And I haven't really had the courage to do that until I came here. And I wish I would have had the opportunity and courage to do that earlier.
And moment 7. Please complete the following sentence. Thanks to my studies, I know that...
I know nothing.
Well, Markus, my impression is a very different one today. You know quite a bit. And we are so glad that you are so willing and so inspiring in sharing that with us and our audience here. So thank you very much for our conversation. It has been a true pleasure meeting you here in Stuttgart again. To our podcast audience, please stay healthy, stay good, and most of all, stay tuned for our conversations that are always based on what is made in science.